Okay, dear student, let us see what is there in this question now. Cold milk enters a small sterilizing unit and flows over an electrical heating element as shown in figure. The temperature of the milk is raised from 11 degrees. So here it is entering at 11 degree and it is leaving at 84 degrees centigrade. A mass of 55 grams of the milk enters every second. So this is another way of telling you the rate of flow of mass. So be very careful. The rate of flow is given. Okay. Specific heat capacity of the milk is also given, which is 3.9 kilojoule per kg Kelvin, and all the units are SI. The only thing is that kilo have to be converted into thousand. Estimate the power input to the heating element. State an appropriate unit for your answer. Okay, so the question says, be very specific about it. The question is, estimate the power input to the heating element. So, what is the power input? Obviously, the heat which is taken up by milk should be regarded as the energy taken up by the milk. It is not the power which is given to the heating element, but we can just assume it that 100% of the energy which is given to the heating element, it is transferred to the milk, so that the same amount of energy is used to raise the temperature of the milk. Accordingly, we would be using the formula for like Q is equal to mc delta T. But the problem here is that heat is not given, mass of the milk is not constant, it is a continuous supply of milk from here, but the rate of mass flow rate is given there. So it means that we must talk about rate. It means we have to divide the whole equation divided by time, something like that. So that will come out to be delta Q divided by delta T. So this mass is a variable here. So this can be written as this. So this is the rate of flow of mass into the specific heat of the milk into the change in temperature of the milk. So this is what we will do. Although this is not a rule, this is not a formula that you would be using delta T like that. It just comes out of experience. Like you would be doing more questions. You will, in the first place only, you will come to this conclusion that okay, fine, here there is a mass flow rate, so it will be delta m by delta T. In many places, when you will be talking about the rate of cooling or rate of heating, then you could be clubbing this delta T under the delta capital T. So delta capital T divided by delta T is the rate of change in temperature. So it means it is the rate of cooling or it is the rate of getting heat, isn't it? So that depends upon the question. In this case, we are not concerned with the rate at which the temperature is rising or something. We are not concerned with that. So we are concerned with the mass flow rate. So we choose to keep this delta T under delta M. So that will become the mass flow rate. And overall, the mass flow rate is already given to us. So this delta Q by delta T, the unit will be joule per second. So that becomes watt. So I can say this is the power, kind of power output, no doubt about that. Mass flow rate is given as 55 grams. So 55 divided by 1000, and per unit time, that is in 1 second, this much is going. So that is mass flow rate. The milk is like 3.9 into 1000 is delta C. And along with that, delta T is 84 minus 11. So 84 minus 11 need not to be converted into Kelvin, because if you convert 11 into Kelvin, you will add 273. You convert 84 into Kelvin, it is again 273 had to be added there. When we subtract them, 273 is getting cancelled. So overall, the difference doesn't change. So when you're talking about delta T, you can keep the unit as degree centigrade or you can convert into Kelvin. You would be getting the same answer. So I'm just subtracting 84 from negative 11. Okay, so with this, we can say that the answer will be 0.55 into 3900 into 84 minus 10 is 74 minus 173. So this is going to be the answer for us. And okay, so I would be having calculator now. 0.055. Okay, so I'm getting the value as 15 kilos, like 15658. So according to me, the answer should be this much. But let us see what is the answer given in the mark scheme. Okay, so the answer given in the mark scheme is this. So energy required for the milk entering in 1 second, the mass into specific heat and into 73, which is 84 minus 11. So technically they have done exactly same thing that I have done, and that is the energy required in 1 second. So that will be written as the power. So they are choosing it to be 16 kW, and I am getting 15.6 kilowatt. So approximately we can say that, yeah, you're getting the correct answer. But there is a difference. This is the heat which is taken up by milk, but the question was what is the heat given to the heating rod. So there will be difference between them. Obviously there will be some losses. So this answer is absolutely correct. It can be reported as 16 kW. Let's move to the next question now. Outline whether your answer is likely to overestimate or underestimate the power input. So, in part A, we are basically having this assumption that 100% of the energy given to the heating rod has been transferred to the milk, but that is not the case. So, definitely, heat given to the milk is lesser than the actual heat that was given to the heating rod. So, the answer here is clearly an underestimate of the power which was actually given to the rod. So my answer will be underestimate. Yes, for 2B, it is underestimate. Let us now move to C. Discuss with reference to the molecules in the liquid the difference between the milk at 11 degrees C and milk at 84 degrees C. So, my dear student, this question is from, you can say, Boltzmann equation for the average kinetic energy. So, it is known that average kinetic energy per molecule, it is given by 3 by 2 kbt. 3 by 2 kbt. So this is the formula for the average kinetic energy of one molecule, average. So it's found to be directly proportional to temperature. So you can clearly say that at 84 degrees centigrade, the average kinetic energy per molecule will be higher than what it would be when the temperature was 11 degrees. So this will be our answer. Let's see what is the answer. The temperature has increased, so the internal energy is more. Average kinetic energy of the molecule has increased. The temperature is proportional to average kinetic energy. Exactly the same thing that we were discussing. Let us move to the next question. Okay, the milk flows out through an insulated metal pipe. The milk is at a temperature of 84 degrees centigrade. A small section of insulation has been removed from around the pipe. Okay, so this diagram is not that very clear, by the way, so the students would be getting confused like what they want to draw here. Let me show you. This is the inlet of the pipe, and so the milk is entering from this end like this. So milk is entering from this end and it goes like this, and at this point the milk is getting out. At this point the milk is getting out. Now this is the insulation that is there. So clearly there will be some inside of a pipe, like thickness of the pipe will be there. So this is inside of a pipe and this is the outside of a pipe, and inside the milk is moving and the temperature of that milk is 84 degrees centigrade. Clearly the milk is just going towards right hand side. So the length of that pipe is 0.56 meter, for which the insulation is broken. Clearly some heat will be lost because there is no insulation there, isn't it? Let's see what are the questions now. This is just for the description of the statement. State how energy is transferred from the inside of the metal pipe to the outside of the metal pipe. Okay, so the metal pipe is thicker. Overall we can draw it like this. So this is the inside of a pipe and this is the outside of a pipe. So inside of a pipe we now clearly know that the milk is maintaining the temperature of 84 degrees centigrade, and so some heat is transferred here, and the outside of the pipe is maintained at obviously, like, it will be some temperature lesser than that, but we will see if that is required in the question or not. We can just imagine it will be like nearly 83 degrees centigrade. So the first question is how the energy is transferred from the inside of a pipe to the outside of a pipe. Obviously the pipe is made up of a metal, and there are only three modes of heat transfer. First one is conduction, which is usually like the popular mode of heat transfer in metals is conduction. Then there is convection, and the third one is radiation. Obviously, this talks about the conduction. So here our answer will be clearly conduction. Okay, so they are like how the energy is transferred. They are clearly referring to the modes of heat transfer there. Okay, nothing more. Like whenever it's written how, you need not to explain it like you have to write a paragraph there. You can just say that okay, conduction is taking place. Need not to explain what is conduction. Now, I will check the answers later, no problem. Let's move to the next question. The missing section of the insulation is 0.56 meter long. The external radius of the pipe is 0.067 meter. The emissivity of the pipe surface is zero point 0.4. Determine the energy lost every second from the pipe surface. Ignore any absorption of radiation by the pipe surface. Okay, but they have not given us that due to the conduction, what is the temperature on the outside of the pipe. Like they are saying the pipe is at the temperature of 84 degrees C. So we can just assume that outside also the temperature is maintained at 84 degrees C now, because the other temperatures are not given. So I would be using a formula here. Now, the formula for this is, I would be needing the diagram. Yeah. So the formula for this will be that we have used in the for the black bodies, and this formula has been used by in the optional astrophysics. It is called luminosity of a star. It is the same thing. Okay. So the power is given by E sigma a t raised to power 4, where E is the emissivity, because we are not talking about a black body, so emissivity is not 1, and emissivity is given as zero point 0.4. Clearly, we're talking about a gray body. Sigma is the Stephen Boltzmann constant, 5.67 10 power negative 8. A is the surface area of the radiating surface from where the energy is radiated. In this case, it is a surface area of the cylinder. This is the surface area of the cylinder, and the surface area of the cylinder is given by 2 pi r L. So if you don't know, you have to note it. 2 pi r is the circumference of the circle, multiply by the length of the cylinder or the height of the cylinder, you get the area. So that value will be substituted here. Temperature is 84. Let us see what is the answer that we are going to get here now. So the power is 0.40 into 5.67, 10 raised to power negative 8, into the area, which is 2 pi. Radius is this external radius, so we will choose it to be 0.067, and the L is 0.56. Be very careful, everything should be in meters. Yes, so this is the area. So E sigma A T raised to power 4, temperature is 84. We have to use the Kelvin value here because it is raised to the power 4, and we are not talking about the delta T in this case. Clearly, we would be converting it into Kelvin. This is the equation that you would be solving with the help of your calculators, and you will get the answer. We, in this video, would be referring to the mark scheme. Let's see. Yes, this is what they're doing. Okay, so the first part, the answer is conduction or the conductor through the metal, and that's it. Now, the power formula is given E sigma A T raised to power 4. Temperature is taken to be 357, that is 273 plus 84. And area is 2 pi r L. And there we go. Substitute the value there, and you would be getting the answer 87 watts. So you have the calculator there, pause the video, and you can calculate it, and you will see that yes, that is the answer. Let us move to the next question now. Describe one more method by which the significant amount of energy can be transferred from the pipe to the surroundings where there is no insulation. Obviously, there are only two modes of transfer that are remaining. Both of them can occur when the pipe is surrounded with the air. So the first one will be convection, and the second mode will be radiation. By the way, radiation is already there. In the second case we have already done, but one another method. So one another method will be convection. I would like to tell you something about the convections now. Convection is a mode of heat transfer in which the medium is coming in contact with the pipe. The molecules are getting hotter, so the air near the pipe is hotter, which is having lesser density, and that is why it just flies away, and the colder air is going to come back to into the contact with the pipe, and thereby taking more heat, absorbing more heat, and even that will move away. This process is called the convection. Convection does not have any formula. These are really, really very complex phenomena, and the formulas are really very complex. We do those formulas indeed in engineering, in later hours, in higher engineering classes, but not at your level, because those formulas are very, very cumbersome and complex. It means that throughout your syllabus, whatever you do, you will not be getting any numerical based on convection. So only the question regarding convection could be whether the convection is taking place or not, and that we can easily see. Okay, dear students, so this is the answer, and that is the end of the this question. Clearly, even in the answer scheme, it is convection is likely to be a significant loss, and there is nothing else there. So this is how we do this question number 2, and after this we would be moving to the next question. Okay, dear students, all the best. Thanks for joining. Bye.